like using more or less complex correlation or statistics. That's the setup that most of us consider to be narrow AI machine learning. Now, related but not exactly the same is multitask learning. So this is, it can be ambiguous, but in a usual setup, you would take a model and you would try to train it so that it solves multiple tasks. So it tries to, let's say at the same time you do the segmentation, you do the classification of day and night, and also you classify or detect objects in the images. So these would be 3 different tasks, and the model should be able to learn how to do it at the same time. Now, this seems similar to continual learning. The main difference is that you don't know in continual learning all the tasks in advance. This comes as time goes by. Here in multitask learning, you know them all the way. So you know all of them at the same time from the beginning. The idea here is that you share the weights. In this multitask learning, you share the weights, and therefore you are able to generalize well. So you build some internal representation of the outside world, and that helps you with multiple tasks. Another related topic is transfer learning, so that you have one task as a starting point, and then you transfer, so you do a fine-tuning on a new data set. So that's a fairly standard way when you, for instance, have a big data set available to you, and then a smaller data set of your final application that you need to use your model in. And that would be like the use case that you would train it in is you take the big data set, you train it, and then you fine-tune the last layers on this new data set. And that's again different because you're freezing most of the time, at least. You freeze the deeper layers and you just fine-tune the last one so that it works. Domain adaptation is a setup where you have a new data that differs in the domain of the data, but the tasks remains the same, but the domain of the data differs. For instance, you have data that was captured during the day, and then at night you want to do the same thing, like detect, let's say, objects in your images, but now all of a sudden the data is all dark, or there is some artifacts coming from the registration process of cameras in the dark. Another related field is meta-learning, where model is trained along with another algorithm that helps this first model to train. So it's like learning how to learn. That's not explicitly linked to continual learning, as you have usually 2 models that interact with each other, but still you have some input on how the models are trained. Online learning, that's a good example where you have data also considered as a stream, but then there are no new tasks as in continual learning, so there are no new problems to be solved. And then continual learning, which sort of you can think about as combines all those fields together into a one umbrella, where you have both tasks and data available as a stream. You cannot move back to the previous data, you cannot move back to the previous tasks, and they fly in as you train. And then there is something that is not on the slide, but it's like open world learning, when you just go out in the wild and there's no information whether you're training or testing. Like in all the setup that you have seen here, you have a clear distinction between the training and testing stage. Now in real world, there's no such thing. Like, I mean, maybe in classes where you have the lectures and then there will be assignment. But when you go out and you live outside, you usually just acquire the knowledge, and just as a constant feedback loop, you train and test your models. And that's, I would say, like a holy grail of what we're trying to simulate here. Okay. So, continual learning as such has several challenges and several problems that we try to answer, and that's why we come up with those different models, methods that you will learn about during this course. And although it sounds straightforward, like continual or lifelong learning, the challenges are quite problematic and still to be solved. The main challenge that people started to observe when they looked at this lifelong learning or continual learning is catastrophic forgetting. And the forgetting is something that you already, I try kind of explain to you, like you have one task and then you have the second task, you need to still know what the first task was about, you forget about it, you're done, boom. Since it's, machine learning, people have big egos and they had to name something a bit more spectacular than just forgetting, so they name it catastrophic. Now it sounds like, you're losing everything and you have to go back home, so that's the reason why we call it catastrophic forgetting. But, another maybe less funny explanation is that this forgetting appears very abruptly, so it's super fast. It just goes straight down to zero when you train your model on the new task. And then the reason or the situation when this occurs is that when data is seen by the model is considered as a stream, it's not stationary, and it cannot be sampled to assume that it's independent, so identically distributed and independent. That's where this IID condition does not hold. So how does it look in, practical application that I guess you will go through in the classes with Wojtek? In a regular setup, you would have like MNIST, handwritten digits as your data set. You would train your network with, epochs, and you would just feed them more and more data, assuming that you will get to accuracy on your test data set around 100. Like MNIST is a fairly simple data set, so everybody would expect you to get almost 100% accuracy on that. Now let's imagine that you split that into tasks. So you don't see this data set as is, you have it as a separate chunks, 0, 1, 2, 3, 4, 5, and so on. Now, if you look at the performance of your model, when you do this split, you will see that the blue one that corresponds to task 1 drops significantly once you start training on the second task. So once you move from 0 to 1 to 2, 3, all of a sudden your network sucks at 0, 1. That's why it's called catastrophic. This drop, as you see, is super steep and you lose all the capabilities straight away. And same thing happens to the other tasks. So forgetting is in general, sure, yeah.
Do you generally consider learning for only, because do you consider this problem for completely different tasks? Because what you've shown so far is that if you want to train on a basically different class within the same task, then it occurs, but do you also consider like learning completely different tasks? For example, image recognition and object detection or something like this?
Yeah, I will talk about that. I think at the end of the evaluation, there are scenarios that assume this sort of task fellowship. It's called, like you have sequence of tasks that are very different from each other. Like they actually expect not only different class, but also expect different output. This is more challenging than this. So the idea here with how we try to approach this grandiose plan of building artificial general intelligence is first start smaller steps. And if the model fails on this simple setup, where you have different classes and of the same data set, and it fails already on that, this means that we cannot move to even more complex tasks. So that would be like my answer. In general, yes, you could consider more diversified set of tasks, and that's the ultimate goal. But to make it, sensible, this path towards this ultimate goal, we start with the simpler solutions or simpler scenarios. So catastrophic forgetting is fundamentally linked with how neural networks are trained, so with gradient descent. And if you look at the, let's say, two tasks and their optimal spectrum of parameter space, if you start with random initialization and you want to find the solution of task one, you can imagine that you go along the gradient to this certain point of your parameter space. Now, if you want to go from task one to task two, you would probably move along the gradient of that second task to some other place. And I mean, obviously, the different parts are not optimal for both of the tasks. That's why you have this forgetting that you observe. Now, if you put all of them together, so task one or task two, like you put all the data together, you would do some sort of averaging, and then you may end up, and that's what happens in practice, you may end up with something in between, which is not so optimized for task one, not so optimized for task two, but there's no forgetting at least. You get decent results. So why this happened? Well, gradient descent is probably the most relevant reason. But if you enumerate the reasons or the symptoms of this happening, you would look at the weight drift, so the weights, the parameters of the network drift between the tasks. That also corresponds to activation drift, so the activations of your network would also drift, so the last layer responses would also drift as you change the tasks. There will be a intertask confusion, so in case of standard learning, you would get all the classes at once, so you would know, for instance, how to find the differences between class number 1, class number 2, class number 3, and class number 4. Like you would straight away understand that the data set gives you the information about differences between all classes. Now when you do it sequentially, and you need to first learn how to differentiate between 0 and 1s, and then all of a sudden you need to learn how to differentiate between 2 and 3s, this information requires you very different borders of your decision boundaries, I would say. So they don't correspond to each other. That's why it makes it so problematic. Another problem that we observe is the task recency bias, which means that in principle the most recent tasks are the mostly so the model would confuse your data with the data that has been seen more recently. So this forgetting is sort of gradual. Like if you look at task number 4, this is the confusion matrix here. In the task number, in the fifth predicted label, let's say that you go from 1 to 5. If you look at the fifth test case, when you want to classify as 5 or something else, you would usually get the confusion along the last provided task by the model. So the previous ones that you gradually, sequentially were shown are much less confused. It kind of concentrates around the last classes that the model was shown. So another way of looking at this problem is from the stability plasticity dilemma. So if the general intuition here is that your network, you can think about this as a neural structure that is stable and plastic. So when it's plastic, you can modify the weights. When it's stable, you want to keep them constant. When you observe new samples, what you would like to kind of intuitively constrain your model to is that on the parts of the weights or the parts of the model that are relevant to previous tasks, you want to keep them stable. So you want to make sure that the weights, for instance, of a model do not change that much if they're relevant for the previous tasks. But on the new tasks, you want to be plastic. You want to be, you want to respond to the gradients on new data. You want to respond to the changes that are related to new data sets. And this can, be conceptualized also as a transfer inference trade-off. So when the samples from previous tasks and the current tasks have gradients that are well aligned to each other, that's good. Then you have this, correlation between the different instances of tasks, and you go the same direction of your gradient. Now, when they show you two different gradients, then there's a problem, especially when they're split in time, so you cannot average them out within a batch. And that's why you start to look for two different solutions in your parameter space, and you go in two different directions. So the possible results of continual learning when you look at the accuracy of your models are the following. If you look at the task number 1, the performance on task number 1 is, let's say, max, or 100, well, 100% is not a, let's say max. Let's say like it's a unit vector that it goes to 1. Then when you train on task 1, your performance is maxed on task 1 and then very low on task 2 and 3. Now when you move to task 2, you observe improvement of your performance on task 2, but on task 1, you start forgetting. So you reduce your performance. When you move to task 3 performance is boosted, but the other ones are getting slowly diminished. When you have no forgetting, then you would have, maybe too much stability first. So too much stability first. So when your model is too stable, that means that you constrain it very much to be very good at the first task that he or she, the model, observed. So you would make sure that it doesn't change with the task number 1. It maxes out on task number 1, it doesn't move at all for the next tasks. That means that it's not good on the elasticity or the plasticity side. Now when you have no forgetting, that's already great. Like you moved past the catastrophic forgetting, which means that when you acquire new knowledge, it goes to the top level, to the max level, and after the next task, you would just equalize all your performances. That's already good enough for most of the problems. What do we want to, and that's where the forward and backward transfer kicks in. What we would expect the models to do, as like humans and Latin languages, we would want them to transfer the knowledge forward. So when you train it on the task number 1, you get this performance maxed out. But then when you train on task number 2, you don't want only the task number 2 to be maxed to the same level, but also past this point. So you actually want to accumulate this knowledge and use it for the better performance of your future tasks. And for the backwards transfer, it's similar, but the other way. So you want to optimize your models, your tasks that you've seen in the past, so that they go above this model max. Okay, so scenarios, how we test our continual learning models. I would say there are 3 main established ways that if you look into literature, you would most likely hear about. These are incremental task, incremental domain, and incremental class learning, or continual, like incremental continual here is exchanged. So in incremental task learning, you would have, task number 1 is 0, 1, task number 2, 2 and 3 in your MNIST, and you know exactly when the task changes. So you are given the model, and you say, now you learn 0s and 1s, now bam, task number 2, this is the second task that you need to learn, these are your labels, now be trained on task number 2. The incremental domain learning means that you don't know where you are, so you don't know exactly that the task has changed, but the domain changes, which means that the 0 and 1 come into 2 and 3, so that they are different. I mean, there's a different domain, but the number of classes still remains the same, and here you still want to differentiate between those two classes. So you want to change your domain, but the task itself, it remains the same as a general concept that you're getting. And then in the incremental class, you don't know that you change the task, you don't know that the task changed, and you have new classes coming in. So that you need to not only detect that there is a new class, or a new task, but also you need to expand your possible output range to 2 and 3. So in other words, you had 0 and 1 as your first point of reference. Now you're kicking in 2 and 3, and the model needs to learn, oh, okay, there are 2 and 3s. Now I need to extend my potential output set to 2 and 3. Now I have 4 classes, and I need to know that my model now is expected to give you from 0 to 3 all the labels. Another way of defining the split is based on the multitask or single task scenario, so single head and multi-head. And in multi-head, you would have a specific head for a new task. So if you have a model of your neural network, for each single new task that will kick in, you will get to add an additional head that is only focused on a given task. And then you need to find a heuristic on how to use a specific head of your network. So in a sense, that would be expanding your network architecture for the new tasks. And single head, you want to use the same architecture for all the tasks. So I think I kind of hinted it before, but just to make you or help you to realize how difficult of a problem we're setting in this class incremental scenario, what we're expecting the network to do is to first have task 1, where it needs to discriminate between triangles and squares. Then we're adding more data, new data on task 2, with the triangles rotated and the rectangles also rotated. And what we want to have is to, after those 2 tasks, we want the model to not only find the differences, the borders between those classes in a separate manner or like individually, but we want the model to figure out the differences between all the classes altogether. This is pretty challenging. Like if you even as a human being, if you tell the baby to discriminate between apples and oranges, and then you give them like cats and dogs, now it's a different focus when you have a specific set of objects to discriminate against, and now you need to figure out what's the general rule between all of those objects and how to discriminate and how to differentiate between them all together. And that's what we're expecting from our models. Okay, so slowly getting to, I would say, the evaluation part. I think we covered more or less what's the definition of continual learning, what are the specific testing scenarios, what challenges are we facing, and what are the problems that we are expecting the network, the continually learned network, to solve. Now the benchmarks, so the data sets that we use to evaluate that. And this again is a fairly complicated topic because the continual learning as a domain is fresh and new, and that means that we don't have that many benchmarks. Even within our NCN-funded project, we defined one of the tasks, research tasks, to find the benchmark that is, I would say, more appropriate to what we want to really measure. But this overview will kind of help you realize how much of a baby domain it is in machine learning. How we started the whole, this whole journey, and where we are right now. So many times when I explained the data set to you, I said there's a splitting happening, and this is pretty much the main topic through the first attempts to create those continual learning scenarios. So you take MNIST and you split it, and you call it a split MNIST. Quite straightforward, I'd say. But the idea is as follows. So you have 0, 1, 2, 3, 4, 5 split into tasks, and then they are giving the classes associated with those splits. And task incremental learning with the task, the answer that your model needs to find is to the question, with task given, is it the first or the second class? This is the question that the model needs to answer. In the domain incremental or continual learning, The question is, with task unknown, so you don't know which tasks you are in, is it the first or the second class? So how do you differentiate between those two again? And in the class incremental learning, with the task unknown, which digit is it? So now you have this full-blown question of like, how not only we identify different tasks, but also how do we expand the pool of potential outputs. I think this is the simplest case because you have MNIST, which is, I guess, the simplest data set that most of you have seen. Now, since people were desperate to find new data sets, they came up with this ridiculous idea that you can permute the MNIST, and specifically permute the pixels within the images, so that you create a new task. It doesn't make any sense because, obviously, permuted. Yeah.
Same permutation like for the older.
Yeah, it's the same permutation for all, equally for all samples, but still from the visual perspective, like you don't have a clue which number it is. So all the models that we use for visual perception would not be able to solve this problem just because there's no local correlation within the image. But again, see, people are desperate, they do different weird shit. So that's what they did. It doesn't make any sense from perception perspective, but it's something that people can compare different models against. So they use that for some time. And then maybe just to give you also reference, the question that your model would need to find for a specific testing scenarios and task, incremental learning, given permutation X, which digit do you see? In domain with permutation unknown, so you don't know where the permutation changed, what digit do you see? And in class incremental learning, which digit and which permutation you're looking at. Pretty complex, huh? All right, next, maybe a bit more, it makes more sense. It doesn't make all the sense, but still more sense, is to rotate the images instead of just permuting them. It doesn't make all the sense because of 6 and 9, for instance. That's not helpful, but except for that, it's kind of, well, at least going towards a good direction. Then there are CIFAR data sets. And here you split them also in like classes, and same as with MNIST, with classes and specific tasks. So usually you split the CIFAR 10 in 10 tasks, 1 class each, or 5 tasks with 2 classes. It's useful as a first baseline for your CL model because I guess it's okay to say that on MNIST everything works. Like whatever model you come up with, it will most likely, if you mingle it enough, if you train it enough, it will work. On CIFAR 10, it's not going to be the case, so it's a bit more complex. So what we usually, with our lab, what we do is we don't even bother to show the MNIST results unless this is like some synthetic weird example that we want to show. We go with CIFAR 10 straight away. So that would be, I guess, your baseline model if you want to train your CL model. If you want to go a bit more fancy, then you go to CIFAR 100. Then what people use this for, or how they split the tasks here is either they split the entire data set into 10 tasks with 10 classes each, or they put first task with more classes, like first task with 50 classes and then the next ones with smaller number of classes, so that it kind of mimics the generalization ability of your model. It's also called IE CIFAR. If I see Omniglot, that's, well, similar to MNIST, but a little bit more complex symbols are given in this data set. So that's very same setup. You also have permuted or rotated versions of MNIST. And then we start to get into more continual learning adapted or specific for continual learning data sets like Core 50, where the data set is created to recognize household objects based on 15 seconds video. with the POV object rotation. So that starts to become a little bit more sensible and a little bit more adjusted towards continual learning. And then there's a split between new instances and new classes within your testing scenario. Then there is Open Loris. It's also on videos, stream with only natural objects. Atari, if you like continual learning in the reinforcement learning setup. And there's also one more paper that the recent paper at NeurIPS from DeepMind and the Jagiellonian University that goes along those lines, and multiple other like split, fashion, MNIST, and so on. So you will start, if you start to play with those data sets, you will see that one of the main challenges for publishing papers in this area is that the benchmarks are not well established, and people would always complain that you didn't do experiment on this specific data set that you like. So that's what we get pretty much all the time in our papers when they are reviewed. Like, yeah, you evaluated this on X and Y, but why you didn't evaluate it on Z? And then there's like, a bunch of data sets that you should probably look at and update this list as we go. And that's the question that you had before, like what's the relation between the tasks? Here, as you see, that the task was assumed to be pretty much the same. I mean, the naming is a little bit confusing, but the output was always a classification between, objects of a same modality. If you want to get more general, then you can look at task transfer or task fellowship, so that you not only change the data, but you also change the tasks that you're looking at. It's a bit more related to transfer learning, but still interesting in the continual learning. Okay, so I think given time constraint, what I want to also finish on, it's the evaluation metrics. So you have the benchmarks, you know more or less what the continual learning is and what challenges we have in CL. Now, how do we evaluate those methods when we have the benchmarks? We set up this evaluation scenarios, but what are the metrics that we use to compare the models? And obviously, performance is one thing, so the accuracy of your classification, specifically in a supervised manner. But since we put those constraints, those requirements also on the computational side, we cannot forget about the resource consumption. That includes model size, the memory, and the number of parameters that the model uses, and the efficiency of how we use it. So accuracy answers the question, how accurate is my model? It can be looked at from like different perspectives. So how accurate is my model on a specific task? How accurate is on the past tasks? And how accurate it is on the future tasks? So this is this temporal axis that you should look like, and a metric averages all the accuracies at any point of time. That's a useful metric. The forward transfer metric estimates how accurate your model is on the forward or the future tasks given a current training. Backward transfer is the other way around. And these are the equations that you can implement within your benchmark evaluation. And then memory, which depends on your hardware, but in general it comes up to the question of how much memory your model occupies. In ideal world, you could say that you have infinite memory, but then you have big models with infinite number of parameters. In practice, usually you're constrained by your RAM or memory that you have on your device. So it's only for the fairness that you should compare the models of a similar, maybe not exact, but at least similar memory sizes, so that especially plays a role, and I will talk about that a little bit tomorrow and then on Friday, when you are allowed to replay the data from the past. So you're not allowed to move the time, but you are allowed in some setups, which some people consider to be cheating, but well, that's part of the beauty of CL, that you can define what cheating is, that you have some memory buffer that allows you to replay the data from the past. So if the model does not have any constraints on memory, then you could potentially keep all the data from the past, and that would be not fair. So that's why you should look at memory from that perspective. Then the computation. So you can look at the time. You can look at the increment over time. What is the number of flops? What is the running time? What is the GPU time? All those parameters can be helpful for you to understand if your model is truly better than the state of the art or not. And then the reviewers will for sure complain.
Yeah.
About the previous slide,
Sure.
Those arrows means there is odds and
Yeah, I think the operation increment, so how much the operation are, how many more operations you have, or how many operations you lose or you reduce. This would be probably I don't know, some delta on the number of operations. You have the links to the specific paper that introduces all those metrics, like as a Bible of metrics over here. But just to give you like an intuition, it's related to the change that a new data introduces in terms of the computational cost. There's, forgetting is one thing, but don't forget that it's also like model robustness, the plasticity, capacity, and there are multiple parameters or multiple axes that you can look at your model from. In practice, people use accuracy and something about the model cost or model computational cost. So these are two main axes that you should look at. The rest is, I would say, just decoration, but again, it's a new field, so people try to breach in with their own metrics. Even we had this idea of like coming up with this new metrics that we will publish, and people will tell us, oh, this is the real metric. It's in practice is very hard, because then you always get this reviewer complaint that you came up with a metric that allows your model to look better than the others. So that's not fair, right? So we have to fight with this a little bit. So in summary, the main point of this evaluation is that you should declare what you're evaluating up front and be very specific about this when you're presenting your results. And this can be confusing. It can take a lot of explanation. Usually, even I don't explain exactly what the evaluation setup we used in our paper. I always call up Wojtek or Kamil or other first authors on our publications, because it's very complex on the on the description side. But you have to be upfront about this. You should choose those metrics wisely, depending on the application. So in some sense, in some cases, it's much more important to look at the computational cost, because you're running a robot or you're running a mobile platform that has very strict computational constraints, while this inference time is not that important, or the accuracy is not even that important. Sort of a trade-off that you should look at when you present your results and compare your models. So focusing exclusively on performance is also discouraged, because there's this computational cost axis that you should, or dimension you should look at. Be careful with deriving your own metrics, because it's like changing the rules of the game when you're playing. So that's not good. And that's it for the first day. So to summarize, the continual learning is a new paradigm of sustainable machine learning, like lifelong learning. It's required with most of the real-life applications that have this lifelong expected period of time. Especially when there's a lot of data or limited computational resources. The challenges are mostly related to knowledge accumulation mechanism. So you want to look at the stability, plasticity dilemma, and the trade-offs between the forgetting and backward and forward transfer of knowledge. There are multiple learning scenarios: task incremental, domain incremental, class incremental, that should sort of ring the bell when you hear about those. And multiple benchmarks, some of them make more sense, some of them not so much. And that's, I think, evaluate them carefully. I think it's it for now, and we break for we take a break for 15 minutes and we get back for the exercise session. Thank you so much. Unless there are other questions, yeah, sure.
So I have a question whether there is like a benchmark or papers where so let's say that scenario is task incremental, but the result on previous tasks affects the future tasks.
Yeah, that's. I guess you joined later on, but this is what we discussed when we were looking at the forward and backward transfer of knowledge. So here we define the requirements, and what we're looking at is not only the forgetting of the past, but also transferring the knowledge from the current task on the future tasks and improving the results on the past tasks given what you learned in this current one. And that's visualized here when you're expecting not only no forgetting, so that every single task gets to a decent accuracy, but also when you learn on the new task, you would expect this new task to sort of leverage the knowledge from the past. And that's the backward and forward transfer that you're evaluating in your scenarios. Any other questions? If not, then let's break. And let's take a break and see in 10, 15 minutes.
So the break is in the cubus, one floor below. There you have some tea, coffee, and snacks. And we'll start in 15 minutes. It will be like 4 or 5 minutes.
Does everyone speak Polish here, or someone doesn't?
There are non-Polish speakers here?
Okay. Okay. So we'll stick with English, okay?
So I'll let you start, and yeah, I'll be back.
Okay, so first a few technical questions. It would be easier if you would have a computer today and for other 2 days. So if you don't have access to computer right now, maybe you can group together and sit in front of one. Okay, are you all familiar with Google Colab, or someone needs an introduction? Okay, so it would be great if you would just start your Colab session, and I'll give you a link to GitHub, and you can download today Jupyter.
Maybe switch off the light?
I don't know where the light is, where the light switch is, but yeah, sure.
Is it better? I don't know. No. It doesn't matter. Better? This side. Yeah. Okay.
So just a second. So all you need to do is open a new notepad and start with a GitHub, and here copy paste or actually type this link, and
Can you zoom in?
I'll try. Is it visible for you?
Now it's fine.
As you're trying to log in, please interrupt me if something is not clear. That's probably my fault, because we'll cover only simple things during these 3 days. So don't hesitate, interrupt me and ask questions. Okay, everyone got access? Okay, someone is still fighting with Colab, or everyone got the notebook? Sure, okay. So let's start. First, and the most important thing, change your runtime environment and ask Google for the GPU. You'll need that in a few moments. So here you just select the GPU from the drop-down list and save, and we're all done. And the side question, are you all familiar with PyTorch or not? Okay, that's great. TPU won't be needed here.
I know that dark theme is nice, but it's easier to see on the light because the text then is dark.
Okay, I can change the.
With presentations, it's easier with the light theme, and if you could zoom in,
Sure.
might be possible to see.
Just a sec.
Tools, settings, and site.
Sorry?
O, it's narzędzia, ustawienia, no i będzie w pierwszej zakładce.
Okay.
Tu, no i w pierwszej tam jest ten.
Oh wow. Is it better for you?
I guess. Yeah, a bit better. Yeah. Because the text is dark.
Maybe it's possible to like oh yeah, that's better.
Okay. As you're all familiar with PyTorch, I won't cover the imports. These are just basic imports that you use in PyTorch. We'll use matplotlib to plot the results and NumPy for some utils. So please run the first code, and you shouldn't get error. If you got, then you don't have access to the GPU, and we should fix this. So the first block works for everyone, right? Great. Okay, so the session is gonna cover first of all the definition of model and the easiest way we define a sequence of tasks in continual learning. We'll use MNIST or Cypher10 for the lab sessions. These are two data sets that are sufficient to show catastrophic forgetting and are not that problematic from the computational side. So let's just stick with MNIST for now. And here we define some basic hyperparameters. You can tune them if you want, but these hyperparameters should work and should give you and produce the results I will be showing you. So let's go with the first block, and this is just a basic function to generate data sets. As in all machine learning problems, we need a training data set and a validation data set. We use exactly the same transformations for both data sets. This is not always the case in continual learning. Because in real continual learning scenario, we do not have access to test data a priori, so sometimes we apply different transformations to test set. But that's not the case here, and we just stick with standard transformation. We standardize the data set, and we transform images to tensors, so nothing fancy here. And that's a function we'll use throughout the whole 3 sessions, so get used to it. As Tomek said during the lecture, the most popular benchmark is a split data set type of benchmark, because most of people are lazy and don't want to bother with something more fancy, so we usually take super standard data set and then split it according to classes. One really important thing, these splits are disjoint. It means that if we split by classes and the first class is in first task, then it is impossible that the first class will appear in further tasks. That has some important implications for the models, but we don't have to focus on this for now. So that's a pretty basic function. We just select the indices that has particular classes, and then we use a subset function from PyTorch that just returns a subset of our data set. And as I said, these subsets are completely disjoint. So this way we created a dictionary of 5 data sets, both for training and both for training and for validation purpose. And that's the whole magic about continual learning. We just add another loop over the standard supervised learning. When we loop over mini batches and epochs, then we just add one loop over, and it's just a loop over the dictionaries of different data sets. So nothing complicated. And as Tomek mentioned, we got different scenarios in continual learning. One of the hardest scenario is class incremental, where we have a stream of data, and we do not have access to task ID, which makes it a bit more problematic because the neural network cannot be conditioned on this task ID, and it makes it really hard to classify data. And please, if you have a question, something is not clear, just say it. I forgot to run this code, so no error so far. During the sessions, I drop some useful papers. This is a paper that introduces this split between task incremental, class incremental, and domain incremental scenario. You can read or just skim through this paper, but it's not mandatory, so you don't need to bother. CAI agent. Okay, so this is our main class that we're gonna work in a moment. It's just a class that has some basic methods. We'll store some dictionaries with accuracy. We'll define some optimizer to train our model. We'll define a model which for the session will be just a simple few layer MLP. I guess so. Let me check. Yes. Okay. So here we initialize our network. I'll show you the network in a few seconds. Here we are looking for CUDA, so hopefully everyone got access to it. Just initialize optimizer for the parameters of our model. Since we are working with classification tasks, we're gonna use cross-entropy loss for the optimization. And a funny thing, you can ask Tomek a question tomorrow why it's always the case that continual learning is so focused about classification. I'm really interested what he'll respond. So.
Isn't it that it's easy?
Yes, I guess it's easier to come up with metrics since we got accuracy, and it's easy to show, oh, my model is better because I got higher accuracy than your model, etc., etc.
What I meant is that the task itself is easy, so we can perform it with lower resources and with less time. So and it's almost always possible to do it with some random architectures.
You mean the supervised discriminative task, right?
Yeah. In particular, classification task is like one of the easiest tasks in the area of deep learning.
Yes. I mean, definitely that's the task that we made the biggest progress so far, because generative models are kind of lagged behind a few years behind the classificators. For instance, it's really hard to come up with a solid generative model on ImageNet, which was solved a few years ago in classification settings. So yes, partially you're right, but that brings a few problems, which we probably won't discuss here, but keep in mind that continual learning can be adapted to other domains and other objectives. It's not focused entirely on classification. There are a lot of papers about continual detection, continual segmentation, or continual generation, whatever. You can do continual as long as you can put your data set into dictionary. So. Okay, so I guess I'll discuss the init. We can reset accuracy is self-explanatory, I guess. Train step. So if you've ever made a supervised learning model, you're probably pretty familiar with these two loops, which are kind of standard. And you just iterate over the data loader. You put your data to GPU, use your model to obtain the output for the particular input, compute the loss, use the loss to generate gradient, and backward with the gradient, and perform the optimization step, and you're happy. You repeat this for number of epochs, and number of epochs is a hyperparameter you come up with. And the only difference, as I mentioned, is that in our case, you change the data loader for some time, and what is important, the data loaders do not repeat in the whole process. I mean, I would actually ask a question why it cannot repeat, because it's not so intuitive to me, and I'm kind of arguing with my supervisor about this, because in a real life, could you come up with an example that you encounter some kind of data, you are expected to keep it in your memory for the entire life, and you will never ever encounter that data again?
Can you repeat the question?
Okay. Suppose that the data loader is just a chunk of knowledge that you in your real life encounter. And could you come up with an example of such a piece of knowledge that you encounter in your life exactly once, and you are obliged to remember that for the whole life? I mean, we're at college, so it's kind of...
My PESEL number.
But you can always check your PESEL, and you can rehearse that memory. Yeah. I hope you do. So that's a digression, but what I'm trying to say is that our world is somehow periodic. We got day and night, we got weeks, we got seasons, we got everything. And from time to time, the data set will reappear in our life. And that's currently not covered in continual learning. No one actually bothers to ask a question, okay, but if I see 1 and 2 today, probably I will encounter it in future. And no one actually tries to analyze this problem. So if you're planning to write a paper, go ahead. But, okay?
Can't it be just trivially modeled by sampling from the trained data sets?
Sorry?
Can't you just trivially model it by sampling from trained data sets and decrease the probability of some set after you choose it or something like this?
Yeah, that's...
That would be trivial model of it, so what's the problem?
I guess I don't understand, because what I understand is you propose to decrease the probability of sampling particular data after getting it sampled, right?
Yeah, particular tasks.
Okay.
Yeah, and then it models repeating something in the future, saying that it's less likely to occur after you saw it, but still it's possible.
Yeah, that would be one way to actually simulate this repeating process of tasks, if I understand your what you say.
Yeah, but like, I don't see what's the problem there.
Well, the problem is that researchers currently do not pay attention to this. It's not a technical problem. It's a problem no one actually wants to study this. And
just from curiosity, can you like provide us with example where this actually might be a problem, that actually not taking this into account actually might cause something like not good for training?
when the data loaders do not repeat, right?
Yes.
Well, if you repeat the data somewhere in the future, it usually takes a model just a few steps to regain that knowledge that the model forget during the gap between the first appearance of the data and the second. So catastrophic forgetting is no longer so much catastrophic, and that's okay. I've gone into too much details, but that is my personal opinion, that catastrophic forgetting and the data set that we use, the sequences that never reappear, this is kind of artificial data set and benchmark, and we could actually focus on different aspects of continual learning and not on the catastrophic forgetting. But you've raised a hand and have a question.
What about using this thing to gauge the process real-time data?
Sorry? Could you repeat?
There was like an example of using continual learning to process real-time data. So then the data would repeat itself.
Yes, exactly. But
is it benchmark? It's a benchmark on things like this, or?
well, the one thing is benchmark, and the second thing is real world applications. And these two worlds are completely separate. And usually scientists study benchmarks, which are artificial and have some assumptions, as Tomek discussed earlier. And the real life scenarios are real life scenarios, and you are actually solving a particular problem. And in many cases, catastrophic forgetting is not the main problem. There are different considerations about memory limitations, computational limitations, etc., etc. This is a field that really depends on what you are trying to do. So just keep in mind that these two worlds are separate, and usually scientists publish on artificial synthetic data sets. But oh, sorry. Please interrupt me. I can talk too long about this. So if I'm lagging, just tell me. Validation is a standard validation, as I said. We also do this loop over the different validation data sets and compute the accuracy on particular task at particular time. And we'll get these results in a few moments. And this is probably the easiest MLP you can come up with in PyTorch. So just a few layers, and it starts with the size of flattened image. Since we operate with images and multi-layer perceptron, we have to flatten the data set. At the output, we got just number of classes, which in case of MNIST is 10. And the forward is typical forward. We use ReLU activations and return the output of the last layer. So again, nothing fancy. And
I have a question here.
yeah, sure.
So if I understand that correctly, so in the model definition, you are upfront defining the
Number of classes.
the defined number of classes.
Exactly. That's a really good question, because that's again the same story about synthetic data sets and real-world applications. And in real-world applications, we cannot even approximate the number of classes we are expecting. And in typical scenarios, people do not bother about this. There are some papers that try to tackle this problem, but usually people just assume they know the number of classes they're gonna iterate over.
But also, when we use this categorical cosmos function, we are updating even in the last layer. We are updating the weights for the unknown classes, right?
Yes, exactly. Because we operate here with one-hot vectors. So what the update's gonna do to the last layer, it's gonna dump out the outputs for all the previous for all inactive classes, and that is one of the reasons that we encounter catastrophic forgetting. Just because of this last layer. If we keep the previous part of neural network up to the penultimate layer frozen, we still would encounter catastrophic forgetting just because of this last layer. You can, of course, change the last layer for, I don't know, k-means or some other different algorithm or KNN to actually obtain some kind of classification, but it's not perfect. Okay, time for first exercise. I'm gonna drink some water. Here, Tomek discussed about few metrics that we usually use during evaluation of. Sorry, someone. Oh, it was a chair, right?
Yeah.
Okay. Tomek discussed some metrics that we use during evaluation, and here's the average accuracy. Here's the backward transfer, and based on these two examples and the slide that I'm gonna show you in a sec, please create a function that computes forward transfer metric. In case of forward transfer metric, there's this additional vector of accuracies, b, and the vector of the vector b is just the accuracy of randomly initialized model. So variable array is a matrix, square matrix, t by t, and b is just a vector of length t. So it's all written here. And I'm gonna show you the definition in a second. So that is the definition, and you should write a function that computes forward transfer metric. And you're probably already done that, right? Or not? Yes. Okay, one important question, one important thing to cover. Where's the zoom here? Oops, here it is. This definition assumes the access to matrix that in fact in our code is transposed. So keep in mind that we have transposed matrix. The reason for this is that here in the rows we got next. The first row describes the accuracy we got on the first data set after completing training on the first data set. And here the time of the sequence goes downward. It's kind of weird, and I've transposed this matrix so that time goes from left to right, which is, I guess, more intuitive. So keep in mind that it is a transposed matrix. Okay, so if you didn't finish, I uploaded the solution on GitHub, so you can just reload the page. So hopefully the correct solution is something like this. And please note that in case of backward transfer, we do not compute the backward transfer for the last task because it doesn't make sense, since the backward transfer is a difference between the last column of our matrix and the diagonal of this matrix, and that would be exactly 0 in that case. And in case of forward transfer, we do not compute for the first task, and that was shown in the definition from the index. We started from the index 2, not from the index 1. Okay, these are functions that are used to change dictionary to array and plot some things. We won't cover this in detail. And time to run first experiment. First we need to create a split. In order to simulate the randomness of this sequence, we usually use a permutation of classes and then split this permutation into 5 disjoint tasks. So here I am with my sequence of 5 classes. As you see, they do not intersect, and we can start the training. It's a typical supervised scheme. We get the data set, we split them, we do exactly the same split for validation tasks. We initialize our agent. Here for your forward function, we need to compute the validation accuracy of uninitialized or randomly initialized model. And after that, we start the training on our sequence of tasks. And then this is just plotting. And okay, we can start the training. Are we all on the same page, or you got lost, or you actually finished all the tasks? On the same page, okay. So as you see, we're training our model on one training data set just for 2 epochs. We can do this because MNIST is not a complicated data set, and we got almost 100% of accuracy on validation data set, which is okay. And just wait a second for the results. Okay, here we are. And that plot looks kind of familiar to what Tomek showed an hour ago. and each line is an accuracy of validation data set of particular task. So the blue one is first task, orange is second, etc., etc. As you see, once we introduce the new task, the accuracy drops down immediately and drops down to 0. That is exactly caused by what you mentioned, that if we are using one common head to classify all the digits, we're gonna dump down the outputs of inactive classes. And in this case, only 2 classes at each time are active, and we got almost 100% on them and exactly 0 on anything else. So, if you followed me, you should exactly achieve these results. This is the matrix we are using in continual learning quite frequently. And that's actually the transposed version of the matrix from the slides. So as you can see, the diagonal is the accuracy we obtain on a particular data set or particular task after finishing particular task. So for instance, here the 99 is the accuracy we got on the second, or actually third, if we start counting from 0, data set after finishing third task. So I guess we can agree that our model forgot a little, and here are our metrics that actually confirms this. If we average results at the end of the training over all the data sets we covered, we got something around 20%, which should be attributed only to the last nearly 100% accuracy. That is just divided by 5 different tasks. Our backward transfer amounts to nearly 1, which says that actually we forgot everything we learned. And our forward transfer equals 0.12, which says that on average we forgot, our forward transfer caused us to forget around 10% of accuracy. This is because if we evaluate randomly initialized model on 10 classes, we usually get around 10% of accuracy due to randomness. And that's what forward transfer metric covers. And if you have no questions till this point, I guess we should go to the second task, which will be a bit more complicated. And here you are tasked to change our class incremental scenario to task incremental scenario. And in order to do so, you need to actually change 3 things. First of all, you need to modify the neural network we use. Here, neural network should consist of the output layer of neural network should consist of 5 different heads. So we won't have the problem of dumping down the outputs of last layer because here each head is treated separately, and once we are training on the third task, we do not bother about 4 different heads for other tasks. And this way, we make sure that the only forgetting we actually encounter should be attributed to the forgetting in the main network. So if we forget, that actually means that forgetting took place from the first to the penultimate layer. So that's a different type of forgetting. And we'll see that in our accuracy that manifests itself differently. And once we modify the MLP class and take into account that during the forward we should condition our neural network on the task ID we obtain, then you should modify the validate method and train method to actually input, pass the task variable as input to our model. So as you see, I've deleted the line of forward pass for our neural network, and you need to modify it in order to train it in task incremental scenario. One important issue I would like to discuss here is that in task incremental scenario, as Tomek mentioned, we no longer need to classify between classes that are in separate tasks. So what we are actually interested in is 5 different binary classification tasks. So in order to simulate it in PyTorch, we need to remap the labels, and we do it exactly in this method when we take into account the class splits and map the original target to the remapped version. So in our case, it's either 0 or 1. The split function is almost identical except for the remap class method, and these are all the differences we need to talk about here. So if you have any questions about the task, feel free to ask.
So we want to have a head of depth 1 to this solution.
Sorry?
What we want is to have a head of depth 1 for each task with not shared weights, and everything else should have shared weights.
Yes, the main body of neural network should share the weights, except for the last layer, and the last layer should be made of 5 separate heads, each made of 2 neurons.
What I was trying to ask is why the last layer on, like, why head consists of exactly 1 layer.
Okay, that's an arbitrary assumption. It's the least we have to do in order to create task incremental scenario, but we can go deeper with these layers, and there's no reason why we shouldn't do this. Okay, anyone managed to solve the task? Okay, so I'll just paste the, or maybe you would like to come and show the solution here. Yeah, you can go and we can just change the screen. Okay.
So what I basically did, I took almost precisely the same architecture as before, but I introduced last layers list, which is simply the module list with 2 classes.
Okay.
Does
there a possibility to make the cursor a little smaller?
no. And then basically during the forward I selected as number. And what I've noticed is that I ran it already twice, and the first it was totally different.
It was different
So
from the
first, the catastrophe forgetting was only the first one, and the rest were really, really nice.
Okay. And in the second run?
In the second one, it's totally different, and it's huge forgetting almost all.
Okay. So that's precisely what we wanted to achieve, and that's good because we have a reason to discuss the results. Okay, so you actually made the assignment perfectly. Clap your hands for your colleague. Not this, also not this, this. Okay. I will push the correct solution to the GitHub so you can look at this, but now I'll paste it, and that's more or less looks exactly the same. So we can just run this code. Oh, we cannot. Oh. Damn it. Okay, in order not to waste your time, I wanted to discuss the issue that you discovered. First of all, as you've seen, the catastrophic forgetting is not so catastrophic in case of task incremental learning, and that's perfect. And that's the reason why a task incremental scenario is not so not so challenging, and reviewers usually are kind of hesitant to accept papers with this scenario. The reason why you obtained so different results from the first round and the second is that we got random split between classes, and the actual catastrophic forgetting in task incremental scenario especially depends on the splits you obtain. And it can sometimes happen that the splits are so nice to the model that they do not induce catastrophic forgetting. And from time to time it is possible to actually not forget because your class is aligned in some particular way and they did not interrupt the previous knowledge, etc., etc. So in order to reduce these effects, we, as researchers, usually average the results over multiple class splits. And there's a paper of actually a friend of our lab who discovered that you can actually find a class split that is in favor of particular model, and if you do not pay attention to this averaging, you can kind of cheat in your results, and that is the reason why we usually expect results to be averaged at least over 5 random seeds. If that's not the case, then probably you're cheating in the results. So if you're gonna read papers in continual learning, pay attention to this fact that the class splits should be averaged over over different seeds. The second thing is we trained this model for not so long. It was 2 epochs. Usually the amount of forgetting is proportional to the length of the training. So the longer the training, the bigger the forgetting. And you can investigate this issue just by changing the parameter of epochs or just changing the learning rate, which is kind of connected to this. What I wanted to cover else. Okay. As Tomek mentioned, task incremental scenario is way easier than class incremental scenario because we do not have to come up with features that are important to cross-task classification, and the model only needs to remember how to classify 0 and 1 and how to classify 2 and 3. It doesn't care about classifying 2 and 1. And that's completely different problem than a class incremental problem. Another issue is that you have to put as an input that wasn't. You have to provide task ID during evaluation. And you can imagine that in real life scenario, this is hard to obtain in certain areas. Also, we in task incremental scenario, we kind of assume that the boundaries between different tasks are sharp. And what it means sharp, that at any given point of our stream of data, we can absolutely, with absolute confidence, say which task we are solving right now. And that's not always the case because let us assume that our task is to discern between seasons. And today it's kind of hard to say which season we are actually experiencing. And that's another issue that we investigate in continual learning, that the boundaries between tasks are actually quite blurry. And once we assume that the tasks are kind of sharply bounded, it's way easier to solve the task. So that's another simplifying assumption. And last but not least, task incremental scenario sucks when you have classes that will reappear. For instance, if in next task you'll come up with 1 once again, you will be forced to actually create another neuron for 1 that you probably learned 3 tasks earlier. So that's another problem with task incremental setup. And for today, that's all from me. Thank you very much for all your attention and not sleeping, or at least sleeping that I couldn't see it. And see you tomorrow. Thank you.